I want to just tell you one other way that we can see inside our bodies. And that way is going to break the rule that I told you about earlier on. We're going to use radioactivity again, but this time we're going to inject one of those nasty flavours of radioactivity. I said gamma or X-rays were good, alpha was bad, and beta was bad. But actually, beta is not so bad, because some of these beta particles, which we know are just electrons, are not really electrons, they're anti-beta particles or anti-electrons. Some radioactive materials emit antimatter. And what happens when this antimatter meets matter? Well, something like this. They disappear. The two particles, the beta particle, the anti-beta particle, we call them an electron and a positron, they meet, they disappear, and what's left is a puff of energy, in fact in the form of two X-rays. And importantly, those X-rays come out along a line. What elements can we make radioactive in this way? Well, very, very happily, it's these. Carbon, nitrogen and oxygen are the very elements that we're made of. So if we can make those radioactive, we can see what our body does with those elements and all the molecules that we can make from them. So this could be a really powerful technique. How do we make pictures? Well, we build ourselves a scanner that looks a bit like this. It's just a ring of very small gamma cameras like the ones I showed you earlier, and they just detect flashes of light that come from the pairs of X-rays. But the important thing here is that the X-rays arrive in pairs, so each of these flashes has got a partner, and we can join the dots, join the partner flashes, and we get lines telling us that somewhere along these lines there are radioactive particles. So again, we've built ourselves a way of forming projections. I happen to have one of these scanners with me, or one that I've cobbled together from a scanner that was put on the tip. So over on the left side here, we've got a segment of a scanner. On the right side, the other segment. And I hope you can see, particularly if we bring the lights down, please, that on the projection screen behind, there are lots and lots of little flashes. Each one of those is a high-energy particle being detected in one or other of these banks of detectors. And this pair of detectors is looking for two particles arriving at exactly the same time. It's looking for antimatter placed somewhere in here. Occasionally, we do see a line joining two of these flashes. That's because cosmic rays are blasting us from the ceiling all the time, or from the sky, and occasionally a whopping great big shower hits this side at the same time as this side, and so we get a simultaneous flash. If I was to put some antimatter in here, we'd see a lot more. Well, fortunately, I have got some. Here it is. This is a very small radioactive source. It's sodium-22. It doesn't really like being sodium. It wants to get rid of some of its positive charge, and it does that by spitting out some antimatter. So if I put it in here, you can see that all of these lines point to where the antimatter is meeting matter and producing these puffs of gamma radiation, or X-rays actually, as they technically are. So we can track that around. That's how this technique works, and it's called positron emission tomography, because these antimatter particles are called positrons. We can make molecules like this radioactive in this way. This is glucose. We can replace one of the oxygens with a radioactive component. In this case, we tend to use fluorine to replace the oxygen for biological reasons. And then we see how the body, or what the body does with glucose or sugar. And here's a picture. And the brain at the top of the picture there loves sugar. It uses about 20% of everything that we feed it. And the heart here sometimes likes to eat sugar because it's got a lot of work to do. And then all these other little bits, they really shouldn't be there because the body really shouldn't be using that much sugar. And this is another way, an exquisitely sensitive way of picking up cancer. And in this case, it's a fairly severe liver cancer. And we can pinpoint exactly where those cancers are by taking CT images at the same time and superimposing them, and therefore we can see exactly where those cancers are.